I don't know what year I was trying to make it, but I just started making it year 40 something. Okay, guys. Unit 4 is still derivatives. Okay? We're still talking derivatives. We're going, I can't remember exactly, contextual applications. So today is really a more, not so much mathematical, but interpretive. Okay, what do these words mean in terms of, how does it relate to the math? So, okay, in our last 2 units, let's read through this. We've defined the derivative graphically, algebraically, and numerically. Slope of the tangent line, instantaneous rate of change at a point. Those words should all sound familiar about slope, right? Or derivative. In this lesson, we're going to interpret the meaning of the derivative in a verbal manner, so as it relates to the context of real-world problems. Now, some history here. When Newton was developing his ideas of the infinitesimal calculus, namely when given a fluent, we call this a function, to find its fluxion, we call this derivative, okay? His thinking was concentrated on velocity. That's why you see such a big connection between the calculus realm and the physics realm, okay? But today we know the derivative's importance reaches into so many other areas involving rate of change. Let's look at the Leibniz notation one more time in a different way. He stated that the variable y depended on x, and if y is equal to f of x, then the derivative could be expressed as dy over dx. We use that notation a lot, right? If we allow ourselves to think of d as representing a small difference in some process, we're reminded that the derivative is simply the limit of ratios in the familiar form. So when we talk about dy dx, I've talked about that relating to change in y over change in x, right? It's also f prime of x, or right here, that little triangle is delta, right? And that means the change in y values over change in x values. Similarly, we can read d dx as a single symbol meaning the derivative with respect to x of, and that's what we'll often put in front of something, like if I want to tell you take the derivative of this, I'll put d dx in front. And I'm saying take the derivative with respect to x. Brings us to this new place of understanding the notation d dx of y or d dx of f of x, the derivative with respect to x of y or of f of x. Leibniz notation can be a little cumbersome when you need to specify the exact x value where you need to evaluate the derivative. However, the benefit is you can read so much about the rate of change through this expression. It's easy to write f prime of 3, so that would be the derivative evaluated at 3. But with Leibniz notation, we'll write the derivative dy dx evaluated at x equals 3. And so that these pieces right here are saying the same thing. But this one allows us to see that it's the derivative of y with respect to x when evaluated at x equals 3. Okay? Okay. Looking at some examples. And again, a lot of it is interpretation. Understanding what these things mean. This interprets into free response questions. How would you, interpret something? How would you label something? So, Sean is cleaning out his saltwater tank and needs to drain some of the water in order to adjust the saline levels. If the volume of the tank V is in gallons, is being drained over time T in minutes, what is the meaningful interpretation of the following statement as it relates to Sean's fish tank? So notice there, dV dt, evaluated at t equals 3, is equal to -2. So we want to put this into, basically, what does this mean in terms of Sean's fish tank? Except, I wouldn't say every 3 minutes. At 3 minutes. It's draining, and why is it draining? Negative. It's draining at a rate of 2 what? Gallons
per minute.
Per minute. Okay. Let's see. What do I have? Okay. So my wording is at 3 minutes, the fish tank is being drained at an instantaneous rate of 2 gallons per minute. But, I mean, here's the deal. We need to hear that word rate in there. That is a key word to expressing. So, yeah. So, however you want to write it. At 3 minutes. The fish tank is being drained at an instantaneous rate of 2 gallons per minute. Okay. Page 1 done. That was a good catch up. Still got 2 full pages to do here, but okay. Meaningful variables. Just like any other language course, we need to use proper names, spellings, grammar, conventions. AP Calculus is no different than AP Language. There are many real-world functions that depend on variables other than X or Y or time. Learning to read and write the correct notations will help you succeed on free response prompts, okay, throughout our course. So, read each scenario and write proper notation for the derivative, okay? So, the Alberta tar sands are one of the biggest oil reserves in the world. Yet extracting the fossil fuel costs more than the profits made. If the cost C in dollars to extract a barrel of oil is losing $3 on every barrel, write the derivative. So we're just trying to put this, basically take it out of words and put it into symbols. Okay. They already gave us the variable C, didn't they? They already told us that C is cost, and that's going to be cost in dollars. What else do I need a variable for? The barrel, right? Because it talks about the cost to extract a barrel of oil is losing $3 on every barrel. So I'm going to use B. And that's going to be B for the, I guess I should have put number of barrels. Okay. Now, thoughts of how I can write this?
Cost is $3.
And I would look losing $3 every barrel, yes? That's kind of hints there.
So it means D of B over there, D of C, and then it would be C equals negative 3.
Okay.
No, C equals 1. No.
Well, we don't have a value that we're going to say C equals. Okay, but flip it upside down though, because it's the change of the cost per barrel. Does that make sense? So I'm going to, one way we can write this, and I'll look at a couple different ways, is DC over dB because it's the change in cost per the change in barrel. And that, what is that cost and change, the change in cost per barrel? It's -3. And that's going to be -3 if we label that dollars per barrel. Why can I not spell barrel? 1 L. Okay. She has it as 2 R's, 1 L. I don't know. I'm assuming that's right on how you spell barrel. But I can't spell barrel, I guess. So now, that's one way to look at it. Okay. Another way to look at this is we could also define, okay, the cost is what we're talking about, right? The cost is defined as a function in terms of barrels. And so we could also talk about this as F prime of V. Okay? I think, in all honesty, this is where the Leibniz notation, the dC over dB, is a little easier to understand in this scenario because it gets both in there. But the other way you can look at this is that it's the derivative evaluated at how many barrels. Okay? Now, what am I looking for? Basically, some type of description like that. Okay? That's the key. Okay. B. The Deepwater Horizon oil spill is regarded as one of the largest environmental disasters in American history. The oil leak was discovered on April 22, 2010. BP originally estimated that the flow rate was about 790 cubic meters per day at the end of the first week. Okay. What are some pieces? I mean, right here we're talking about 790 cubic meters per day, yes? So what are some variables we need to define?
Oil.
Well, what about the oil? How is it being measured?
Cubic meters.
Okay. What do we know about cubic meters? That is representative of not area, volume if it's cubic, right? Okay. Because I see that label cubic meters, we're talking about an oil leak, you're changing the volume. It's a volume of oil that is leaking out, right? So, and of course, for volume, we're going to use V. Okay, and that volume is in terms of cubic meters, right? So V is volume in cubic meters. What else do I need a variable for?
Time.
Time, yes. Days is a measurement of time. Now, be specific here, because you'll notice a discrepancy throughout the problem that this label is 790 cubic meters per day. So our time needs to be measured in days. Augie said something about weeks. There's a discrepancy in this problem, isn't there? Are we going to have to be careful? Yeah. Okay. We've got to keep this all the same. Now, in all honesty, it's going to be easier to talk days because can a week be converted to days? It can be. Easier than taking days and converting it the other way. Yeah. It gets more tricky if you're trying to convert to weeks because of the fractions involved. Okay. So, with this in mind, okay, up here, I said cost is defined in terms of variables or barrels. That means this one, what is? Volume is defined in terms of time. So we can think about volume being a function of time here, right? Okay. So, ways to write this.
say dv over dt, and have it down I t equals 7. Yes. Equals 790.
Yeah. So the change in volume over the course of time, evaluated at t equals 7 because it's at the end of the first week, and a week is 7 days, right? And that is 790. 790 what? Cubic meters per day. Derivatives are always, they're always going to be a rate, so it's something per something. No, I don't have it as negative. And I think it talks about the flow rate was 790 cubic meters per day. I don't know. I think it's because it's just flow rate. It's not the fact that it's losing. It's just, in general, this whole problem is about a leak. And so it's just that's the flow of the leak. Okay. The other way I have this is if you look in terms of the function in terms of time, this could also be f prime of 7 is another way you could evaluate, or not evaluate it, but list it. Is it's the function evaluated at 7. Okay? So whether you say f prime of 7 equals 790 or dvt evaluated at t equals 7 equals 790. Both are good. Okay? Ready for the next one? Okay. Population P of the endangered mountain gorilla has an ongoing study tracking the number of gorillas since 1992. The population increased by 114 gorillas during 2003 of this same study. Well, they gave us one variable, right? Or did they give us 2? P is the population. And do they give us, let's see.
Would it just be time?
Okay. And then, yeah, the other piece is it's the population in relation to time, yes. Time in terms of what? What are they measuring time in? Years, right? Because they talk about tracking the number of gorillas since 1992. They talk about 2003. So we are talking about T being time, and it is time measured in years. You always want to be aware of what you're measuring your time in. So if we're defining the function, it's population is a function of T. Okay. Okay. Thoughts on what we're going to do here?
It would be dp over dt, and then y t equals 13.
Yeah.
Wait, 11. Math.
That's why I was coming over here to show that 2003 minus 1992 is 11 there. Okay, so the change in population over the change in time, dv dt, evaluate at t equals 11. And what is this equal to?
114 gorillas per
I believe it is gorillas per year, yeah. It was increased by 114, so that's positive 114. The other way you can express this would be the function, so f prime evaluated at 11. Okay? Again, both are good. What I really need, I need you to be well-rounded calc students. I need you to be able to work with either notation, right? Okay. Now we're going to go the other way.
No.
We're going to have to take what they give us and put it into words.
I don't want to do this.
You like the other way easier? I don't blame you. I like the other one better too, but. Okay. Suppose a planet is discovered in 2024 and is named Newtonia. If the alien population P of T is recorded in millions of aliens, and T represents the number of years since the planet's discovery, explain the meaning of each of the statements. Okay, so did you catch some information? Now, interestingly enough, when she wrote this, 2024 would have been the future. I mean, you know, this curriculum is a couple of years old.
Whoa.
I mean, when I bought it, I've been using it, this is my 3rd year using it. And it wasn't, I mean, she'd already had it written for a couple of years at that point. So, you know, that was the future. Okay, so let's see, what do we know? Alien population, P of T, okay, is recorded how? Millions of aliens. T represents the number of years since the planet's discovery. Okay? So, first one, P prime of 3 equals 0.5. And P prime of 3, if you wanted to change that, that would be what? dp d, what is it in relation to? dt. When t equals 3 is equal to 0.5 or 1/2, whatever you know. I don't know if that helps you or not. I'm not saying you have to do that. I'm just trying to.
After 3 years, 500,000 aliens.
Yeah.
Discovered. Gordon.
At 3 years, the rate of population of aliens being discovered is 500,000 a year.
So, I'm trying to put it all together. We're on the right ballpark. So, in 3 years, yes. Now, you could say in 3 years, or when t equals 3 years. You could also say in year what?
3.
Or
27.
2027, yes. Are you seeing where we're at now?
Yeah.
Okay. So, in t equals 3 years, or in 2027, the population of Newtonia will be, you guys said 500,000 aliens, but what is it doing? It's increasing at a rate of 500,000 aliens per year. Or, what is 500,000 aliens? 500,000. Okay, now, I think both would be acceptable. I have 500,000 written in mine, but, you know, equivalence there. Okay, so, in t equals 3 years, 2027, population of Newtonia, or just say population, you know. Beware, you can't just say will be 500,000. It's a derivative. It's a rate of change. So it's not going to be 500,000. It's going to be increasing at that rate. Will be increasing because we're positive, right? At a rate of 500,000 or 500,000 aliens per year. Okay?
Inverse.
Inverse, what?
Wait.
Maybe that means we just flip them upside down.
No, you flip the
5 in the second one.
yeah.
Well,
Opposite.
so normally in this scenario, your x-axis is your time, right? And your vertical axis would be your population. Inverse switches it, and now we're talking population and time. So the inverse basically now, my population is your input, your output is the time. I don't know. I always feel like these are awkward to state.
At when population is increasing at a rate of 7.5 million, it would be your 5 or something like
Okay.
that.
Time t equals 5 years. The population of Newtonia will be increasing at a rate of 7.5 million aliens.
Now let me pause this. Is this one a derivative?
No.
No. So what do we have to take out? You guys are on the right track.
And they're increasing.
It's not increasing, it's not a rate.
The population is
It is.
7.5 million at year 5.
There we go.
Bingo.
Okay? So mine reads the population on Newtonia will be 7.5 million aliens 5 years after 2024 or in year
2029.
2029.
Just switch.
So you just switch, yeah.
Wasn't that bad?
You just switch it. It's not a derivative, so I don't want to hear anything about increasing, decreasing, or rate of change. Okay? Save those for derivative speak. The population of Newtonia will be 7.5 million aliens. Get that appropriate label in there. 5 years after 2024 or in 2029.
Okay, now. Next one. Screw it.
This is the tricky one
Um,
because when you put a derivative on inverse, there's a little trick to it. I agree.
um,
So, and you guys correctly got it switched that basically this is the population and this is the time. Same thing's going to be true here, right? When the population is 7.5 million aliens. Now, this is the piece they always do a little bit differently in inverses. Okay? So this 0.75 is the derivative now, yes? So now we are talking rate again. Okay? Now, what they do, I just gotta remember how they do this.
did you switch those already or no?
Huh?
Is the 0.75 originally the time?
No, it's because it's an inverse. Right? Kind of like this is an inverse. Anytime it's an inverse, my input and output switch. So normally input is the time, like input is time, output is population. Okay? But because it's inverse, they're flip-flopped. Okay? So here, when our population is 7.5 million, it takes, okay, so how mine reads is it takes 0.75 or 3/4 of a year for the population to increase, and we're talking about in terms of millions, so to increase by 1 million. Okay, so it's because, again, it's always weird how they do this, because realize on an inverse, your output's probably going to be time. Okay, and so it's hard to say at a rate of change of 0.75 year, or 3/4 of a year. And so that's why they always put it in relation to 1 unit of whatever. So 1 million here. Okay? So putting this all together. When the population on Newtonia is 7.5 million aliens, it takes 3/4 of a year for the population to increase by 1 million aliens. Okay, for it to increase by 1 whatever we're talking about. In this case, it's 1 million. As I said, this is the tricky one. Okay, so when the population on Newtonia is 7.5 million aliens, it takes, you can say 0.75 or 3/4 of a year for the population to increase by, and it's 1 of whatever the unit is. In this case, it's 1 million aliens. Okay, we'll talk about derivative of the inverse again before we're done today, okay? Comes back up on number 6, I know. Okay. Next page takes us along the same lines here. Next examples, we're going to show how clues from the units can help you recognize the interpretations of the derivatives as they relate to real-world scenarios. Suppose you launch a water balloon from a giant slingshot. Let S of t give the distance in feet that the water balloon traveled from its initial starting point as a function of time t in seconds. Explain the meaning of the derivative notation. Now, they said S of t is distance, yes? That's how they defined let S of t give the distance. Now, distance, in terms of physics, also is another way to talk about the position. What I'm trying to get you to think about, this talks about S prime of t, yes? What do you know about S prime of t?
Velocity.
It's the rate of the position, or rate of the distance. Better put, it is the velocity. It's v of t. In other words, I'm trying to get you to make that connection there. I know, you guys don't have the physics background. But it's a connection we've got to make. Okay, so what are we going to say here?
Two seconds. Where t equals 2. It's traveling at a velocity of 38%.
Okay, what is it? What's traveling?
I have no idea. Oh, water motion.
Okay, reread this prompt, right? Okay, so when t equals 2 seconds, the water balloon is moving. Now, I forget, did you say velocity or speed? Okay, velocity. What type of velocity? Officially, this is an instantaneous velocity. I don't know if you officially have to say instantaneous or not, but because it's the derivative at a point, it's instantaneous.
So 2 seconds, it's moving at 38 feet per second.
Pretty much. Yep. When t equals 2 seconds, the water balloon is moving at an instantaneous velocity of 38 feet per second. You always want to relate back to the prompt. What is it we're talking about here? Okay? So, when t equals 2 seconds, the water balloon is moving at an instantaneous velocity of 38 feet per second. Okay? Next. The total cost C in dollars of an airplane flight is a function of the number of passengers in can be calculated by derivative airlines using the function C equals F of N. What does it mean to say F prime of 182 equals 58?
When there's 182 passengers, the cost of the flight is $58 per person.
What did you say there?
So, if there's 182 passengers, they can fly for $58 per person. Or per passenger, I guess.
Except, remember it's a derivative here.
The rate.
The rate is changing $58 per passenger. Okay?
Yeah. Yeah, for sure.
So the rate is changing. When there are 182 passengers, the rate is changing $58 per passenger.
What's the rate? The rate of a ticket?
Yeah.
Flight?
Yeah. The rate in terms of the cost. So I guess you could say, I just have it as rate. I guess I have two different descriptions, but when you say that 58, it's 58 what? Dollars, right? So when you put that dollar sign on there, that kind of takes care of it. So. When there are 182 passengers, and you could say the cost, the rate, I don't know. The rate is changing $58 per passenger. Okay. Ready to talk about water? What'd you say? Non-potable water. Okay, non-potable water is being pumped into a processing center where the depth in feet of the water at a time t in hours is given as y equals h of t. Interpret the following statements using the proper units.
Okay.
Depth is in feet. Time is in hours. H of t.
7 seconds or hours. Oh, sorry, at 7 hours. The depth is 5 feet.
Realize that 7 is time, right?
Yes.
And this is your depth. So yeah, at 7 hours, the depth of the water is 5 feet. I wanted to be specific, the depth of the non-potable water, but
And then at 7 hours, the water
No.
is
Depth of the water is changing at a rate of 6.6
6.
feet per hour.
Oh, yeah.
put it all together and yep, at 7 hours, and I could say at t equals 7 hours, but let's see. I have mine as the depth of the water is increasing at a rate of 6/10 feet per hour. So at 7 hours, the depth of the water is increasing at a rate of 6/10, what did we say, feet per hour.
All right. Okay. When the depth is 7 feet, or it takes 9 hours to get 7.
Yeah.
I don't know how to
Up to
put that.
7
I don't know how to
feet,
put that.
it will be.
So it take 9 hours.
Take 9 hours to get to 7
At
feet.
9 hours, the
Yeah.
At hour 9, the depth is 7.
And I will say, there's not a derivative or anything, so it's just at this is happening, you know. Mine honestly says after 9 hours the water is 7 feet deep. I probably would have said the water is 9 feet deep at 7 hours is probably what, you know. I said that backwards, didn't I?
Yeah.
Okay, sorry, I got my numbers backward. So, okay. The water,
At 9 hours, the water's 7 feet.
right,
Water
which is
7 feet deep.
right. Either way there.
Yeah.
Okay. It's not a change, it's not a rate, it's just is. The water is 7 feet deep at 9 hours. I don't know why inverses are so hard for us to think, but it's hard for me too, as you can tell, as I just got them confused. Okay, so okay, the fun one.
No. It would just be at 1.4 hours, the depth of the water is increasing at a rate of 7 feet.
When the depth of the water is 7 feet, it takes 1.4 hours
To increase by
to increase by a foot.
You guys are relating it back to the one we did earlier,
Yes.
right? Okay, so we have to realize that 7 is our input here, and that's the height, right? What's our rate is the 1.4, and that is our time. Okay, so the input that's given is when the depth of the water is 7 feet. Then it's weird to say that it's at a, rate changing 1.4 hours. So that's why it's 1.4 hours for the depth to increase 1 foot more. Okay. When the depth of the water is 7 feet, it takes 1.4 hours for the depth to increase 1 foot more. Okay, guys. Homework? You're not really doing any math.
Yes.
Yeah,
Of course, I'd rather do that.
I'm kind of with you there. That's a personal opinion, of course, but you're writing out explanations. Okay, you're putting it into words is a lot of what you're doing there. Okay,
It's like-
so work to understand the
Puzzle.
explanations.
Puzzle.